Today we're looking at parallel lines and what happens when we cut them up into proportional parts. Now, most of the time we'll see this in terms of a triangle. So if we have two of our sides for similar triangles, like in our diagram for triangle ABC, but we have two parallel lines. So if, for example, DE and AB were parallel to each other, then it actually does two different things. So it separates the other two sides in a proportional manner. So if I had segment AD compared to DC, I could compare those in the same fashion as CE compared to EB. Now we can only write this proportion if we know for a fact that those two lengths, those two segments DE and AB are parallel. If we don't have that marked, then we can't compare those portions. So if you remember in our last video, we did have some overlapping triangles, but we took a step back and looked at the full triangle altogether rather than the individual pieces that the different sides were broken up into. It does also still create two similar overlapping triangles. So we could still use the same ideas as before. We could do or compare segments DE and AB in a proportion, excuse me. But we'd have to be very careful that we're still using entire sides instead of just the parts like I did in the proportion I wrote down. All right, the secondary piece to this is something called doing a mid-segment. So when we look at that second triangle, if we know that we have two parallel lines again, so I'm going to mark my parallel lines for RS and AB. So if I know that those are parallel, that's given to me, and I know that that line, that segment RS actually bisects the two sides of the triangle that it intersects, then it actually creates something called a mid segment, connecting the mid points. So that's a little easier to remember. And the two big things about this is when that happens, we're always going to have those parallel lines happening again, like we did in the top diagram, but we're also always going to have our triangles with a scale factor of 1 to 2. So a smaller triangle 1 compared to the bigger triangle would be twice as long on all of those sides. So let's look at a few applications of this. Again, we might see this in triangles and we might see this in just parallel line diagrams. So let's look at several examples. So example 1, we're given triangle ABC, and then we have an additional side drawn, segment EF, that's parallel to CB. So if that's the case, then I know I've created parallel lines, I have similar triangles, but I can also now just compare the parts. So all I'm going to do is still make sure I'm going in the same order. So for example, if I start with an 18 and compare that to the 6, along the same side, I'm looking at the bigger side compared to the smaller side. So same thing on the bottom. Bigger side is x plus 22. Smaller side is x plus 2. And then we're going to approach this the same way we did before, which is just cross multiply and solve. So we'll have an 18 times x plus 2 and a 6 times x plus 22. So multiplying that out, I'm going to have 18x plus 36 and a 6x plus, let's see, 22 times 6 gives me 132. And unfortunately, I didn't plan out my space perfectly. All right, combine your like terms, subtract a 6x from both sides. So that gives me a 12x. And then subtract 36 from both sides. Let's see, 132 minus a 36 would give me a 96. And then we can divide both sides out by x. 96 divided by 12 will give me 8. Now, if you wanted to, you could still approach this the same way as previously, and we could look at the sum of each side and do the larger triangle. That just means we'll have a larger expression down at the bottom, but if you wanted to pause the video and try it out that way, check to see if you get the same answer out. Okay, let's look at example 2. So in example 2, same thing. I can compare the pieces only if I'm looking just at the pieces that the parallel lines divide up. And that is exactly what I have here. So I'm just going to compare 24 compared to x equals 30 over 10. Now I'm going to use a little bit of a math trick on this one. And you don't have to do this. You could just straight out cross multiply, solve it out, see what happens. But I'm noticing I have this 30 over 10 on the right-hand side. So if you see things like this, and I know I haven't done too many problems like this, actually I haven't done any problems like this, you know, we could actually simplify this out. 30 and 10, well, I could divide a 10 or simplify out a 10 from both of those values. So I could rewrite that fraction as 3 over 1, still equal to the 24 over x. And so if I do that, I can actually reason through this. Well, how do I get from a 24 to a 3? I divide by 8. So that means my x should be 8. But again, let's see if we still get that solution, even if we do this the same way we did before. So again, cross multiply, I would get a 30x equals 10 times 24, or 240. X divided by 30. So 240 divided by 30 gives me, gives me that same 8. It does not matter which way I solve it. Alrighty, example 3. Same thing, double check. Are you using or are you comparing similar pieces? And so this one's a little different. What's going on with that 33? Okay, so 33 is the entire right side of the big triangle. So I could do this problem two ways. So I could, if I wanted to, find my missing side down at the bottom, or go at this with the 33 in mind. He's a full segment, so let's do a full segment. So let's practice doing one like this. So let's just add these two smaller segments together to make the entire left-hand side. And again, I could do the individual pieces, but again, I want you to get this practice. So if I combine my like terms, well, I have an x and I have an x plus 12, what would that come together to make? So I have 2 x's plus the 12. So the proportion I'm going to go ahead and set up, small to small, big to big. And again, not the only way to do this problem. So if you did want to try to solve this problem out just using the leftover piece, again, if the entire right-hand segment is 33 and the top piece is 11, I could subtract and find 22 for the smaller piece. So you could set the problem up that way. If you choose to do that, go ahead, pause the video, and then come back and see if we get the same answer. Okay, so cross multiply. 33x is going to equal 11 times 2x plus 12. So distributing out that 11, I'm going to get 22x plus 132. How did I do that so quick without the calculator? Okay, your trick for multiplying by 11s, when you multiply a 2-digit number, add the 2 digits together and put it in the middle. So 1 plus 2 is 3, put it in the middle. Already subtract, or to combine your like terms, so subtract 22x from both sides, gives me 11x equals 132. But we know from our previous math that that actually equals 12. Alrighty, so number 4 is a little different. So examples 1, 2, and 3, we had those portions on the right-hand side labeled, and we still have them labeled, but only with congruent marks now. So what was that again? If we know the sides are bisected, if we have a midpoint and a midpoint, what do we know about the two parallel sides? They're the bottom sides of two triangles that have the relationship 1 to 2. So really, if I multiply the top smaller piece times 2, that should give me the larger piece. And now I have a pretty simple equation to solve out. Just divide both sides by 2. We will get a decimal on this one. That's okay. I'm getting 17.5. That's it. Now, if you wanted to fill in other values, you could. If you have these marked as congruent, then they would have that same relationship. But if you notice that you have those congruent pieces on the sides, just multiply that smaller base by 2 to make the larger base. Alrighty. Next example. Same idea, but twisted around a bit. So I definitely have mid segments going on. So if my top two segments here are congruent, what do I have to know about the bottom two segments? Because everything is divided up by parallel lines and we already knew the relationship of the segments that they were creating, we can use the same relationship on the bottom. So 3x minus 4 equals x plus 1. This is the one scenario where you, or with using mid segments, that's the one scenario that you might be setting things equal rather than using a proportion. So be careful. Okay, combine your like terms. I'm going to subtract an x from both sides. So 2x minus 4 equals 1. Then add 4 to both sides. So 2x equals 5. Dividing out, we get another decimal on this one, but he's not too bad, 2.5. All right, so let's look a little bit more at that whole proportional part. So everything we've looked at so far is part of a triangle, but what if it's not? So we can kind of extend this a little bit. So looking at example 6, if you extended your two transversals, so these kind of diagonal lines here, if we continued those on, we'd actually make a triangle. So this really is just kind of an extension of that same idea. So even if it's not a triangle, but you still have parallel lines and they're cut by two or more transversals like we have here. So the top line and the bottom line, those are transversals, the diagonal ones. Then all the pieces are going to be proportional. So a few different proportions that we could actually set up. So if I compare in the first one, B compared to C, well, I need to go in the same order, just on the other transversal. So that would mean Y compared to C. Okay, next proportion. We have A compared to X. So A compared to X. And then our second ratio starts with a B. So that means we'd have to compare him to the Y. Okay, next one, X compared to Z. So X compared to Z, going in the same order on the other transversal, that means what do we have to compare to C? Hey. And then what do you think we should fill into that last ratio to make it work? So and I almost have to go backwards on this one. So think A compared to X. Well, wait a second, we already did that one. That's right above there. So what should we fill into that top portion? Well, that should just be a B. So just because the proportion or the ratio was written in different orders doesn't mean the relationship doesn't still hold true. And so let's look at 7 and 8, or 7 through 10. And again, most of these are parallel lines, but we see number 8, it's actually part of a triangle. So we have kind of nested triangles going on there. But if I have all parallel lines, which I do have marked in every diagram, then that means as long as I'm just comparing my parts in a consistent order, that's going to be a valid proportion to use. So even if you set up your proportion a little differently, double check to see if you get the same answer as I do as I'm going through these examples. Okay, here we go. We are comparing A is 3. So let's go ahead and label our diagram as we go through. B is 8, C is 6, and we need to figure out segment D. And so again, you can get as wild and crazy as you want in your order. I tend to keep to the same side of the transversal if I can. But again, this is only one way to set up the ratio. When you cross multiply, if you still get 3x and 8 times 6, then you have a correct setup. And so 8 times 6, well, that gives us 48. Divide 48 by 3, and we get out 16. And that makes sense with our diagram. You'll notice C was bigger than A, so D should be bigger than B. Okay, example 8. Wait a second, I only have one side of my transversal, or one side of my diagram filled in along a transversal. What do you think the comparison is going to be? So notice on the left-hand side, each one of these sections created is all marked congruent. So what's true about all the segments on the right-hand side? They are also all congruent. And so I could set this problem up a number of different ways. as long as I just have the same variable, I can pick any two statements and set them equal. So I'm going to go with the most straightforward one. Let's go with 12 and x plus 3. Then all I have to do is subtract 3 from both sides, so x equals 9. This wouldn't be a bad scenario. If you're not sure if it's supposed to be that easy, pick a different combination and see if we get the same answer. So let's try 2x minus 6 equals x plus 3. So again, I'm going to subtract x from both sides. So x minus 6 equals 3. And then add 6 to both sides. Hey, we got the same answer out. Either method would work just fine. Okay, what are we missing in example 9? We have 32 is the entire bottom segment. So if we're going to use our shortcut and just compare our pieces, we need to figure out our missing piece. So what do I have to do? 32 minus 18. So that would give me 14. And now I can set up my proportion. So again, any order would work as long as you're staying consistent through the problem. And then when you cross multiply, just make sure you have the same thing as in my second step, which is going to be 18x equals 27 times 14. Okay, so let's simplify that out. 27 times 14 gives me 378. Large number, but if you think we're dividing by 18, it is definitely going to get down to a smaller number, and I get out 21 for my answer for x, which makes sense. The two top segments are bigger than the two bottom segments. Okay, go ahead, pause the video, maybe try out example 10. Okay, example 10 is definitely another proportion problem, just like number 9, except they gave us all the information already labeled. And so I'm just going to start writing ratios. And as long as I'm in the same order, so I started left to right and then left to right, I'm going to cross multiply. So 32 times y is equal to 16 times y plus 3. So as long as you are multiplying the same things, then you have a correct proportion. Okay, distribute out that 16. So 16y plus 48. I'm going to subtract 16 from both sides. So 32 minus 16 gives me another 16. And then divide both sides by 16. And we're getting out 3. All righty, last example. What do you think? Do we need to set up a proportion? Or is this one of those that we can set parts equal? Okay, so you're noticing, hey, I have 2 different variables in here. And so that means I can't set up a proportion. I would need additional information to make that work. But I do have these 2 segments on the left marked as congruent. So what does that mean with the relationship on the right-hand side of the diagram? Those would also need to be congruent. So I just need to set up 2 equations, just setting my x expressions equal and my y expressions equal. So I'm going to go ahead and put the one with the bigger x on the left, and you're going to see y in a second. So 3x minus 1 equals 2x plus 4. Subtract an x from both sides. That's why I put the larger x on the left. Add 1 to both sides, x equals 5. So we could do the same thing with the y's. Again, I'm going to put the larger one on the left, but it really does not matter. And then all I do is subtract 2y from both sides, and I get y equals 2. So again, moral of the story is there will be some similar problems where you can set things equal, but it's only in those scenarios, like this last example, where we have portions marked as congruent, and we're using that relationship. Otherwise, you should always be using a proportion to set up your problems. Okay, let me know if you have any questions, and if not, start in on your practice. Talk to you later.